Alright, so we're going to go over the three basic data structure problems that you have to know. The first one is where you have an array of numbers and you want to find two elements that add to, say, x. So if the array is A, then you have AI plus AJ equal x. And so naively what you would do is you would just iterate over, I and j and see if any of those pairs equals x. And if they do, you return that pair. But the smarter thing you can do is iterate over one of them and notice that aj needs to equal x minus ai. So we can actually just look up x minus ai once we have ai, which we're iterating over. And so iterating is obviously O of n. So what's looking up? Well, we can just create a set or a hash map or something to look up values, and that just gives O of 1 lookup time. But the creation of it is obviously O of n. So O of n. Alright, so let's implement this. Obviously this is an O of 1 operation done n times, so the full algorithm is going to be O of n. So the first thing we do is we iterate over this thing. So for I equals 0 dot 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 n minus 1, ai is equal to ai. And then we look up the next thing. Alright, so in order to do that we have to first create obviously the set or the hash map or whatever. Let's just use a set to keep it simple. So let's say set s, and that's just a set that contains all the elements of A. So all elements of A. Okay, and now we can just look up aj. So if aj is in set, then we can return true, meaning that we found a pair, and at the very end we can just return false, meaning we haven't found a pair of ij that add to x. And so remember, aj is just equivalent to x minus ai. So this is our full code right here. There's an O of n thing here. There's an O of n thing here. Lookup is O of 1. So the whole thing is just O of n, of course. We already knew that. Alright. What happens if now instead of finding two elements that add to x, we want three? So we want sum ijk. Well, we can do the same exact thing. We can iterate, and then notice that ak equals x minus ai minus aj, so we look this up. And so I'm just going to write the same exact algorithm. Alright, so we want to iterate over ai, so for I equals 0 dot 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 n minus 1, iterate over j. For j equals 0 dot 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 n minus 1. And then we want to look up k. So if x minus ai minus aj is in the set, return true. Return false. And of course we need the set to begin with. That's just the same exact thing we did before, so it's set s equals all elements of A. Alright, so this is O of n. This is O of n. This is O of 1. This is O of n. And so these three things make it O of n squared, of course. And that's what we could have expected from the start. We're iterating over two things and looking up a third thing in constant time. So Alright, so we covered 2 and 3 variables. What happens if we have a bunch of them, like k variables, you know, that all sum to x? Well, it's pretty obvious that we just want to iterate over all of them except the last one and then look up the last one. So this is going to be O of n to the k minus 1. Right? We have k of these and k minus 1 iterations. So that's really all I want to say about the first category. So I'll just circle it. And again, this was O of 1 data structures. So hash maps sets we took advantage of. The second thing I want to show you is a variation on this problem. So it's the same exact thing. You have an array of numbers, except this time you want to find the biggest ai plus aj that's less than or equal to x. So all we did was change the equal sign to a less than or equal to, and we want to find the biggest number such that this holds. And so how do we do that? Well, it's the same exact idea. We want to iterate over this, and we want to look up this. So when we look it up, it has to be aj less than or equal. We want to find the biggest aj less than or equal to x minus ai. This is what we're looking up. Alright, so every time you see a less than or equal to sign, you should automatically think O of log n data structure. That just comes up over and over again. So O of log n data structure. And so we haven't talked about how to actually do this lookup, but it's kind of obvious that it's going to involve an O of log n data structure. This means we can use a binary search tree or a sorted list or something. As long as it's log n, it'll be an optimal lookup. And so it's very similar to the algorithm before. We say for I equals 0 dot 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 n minus 1, you know, that's just this iteration part. ai is equal to a of I. Now we want to do this lookup part. Find biggest number less than or equal to x minus ai. And in order to do that, we need a binary search tree, so B equals a binary search tree containing, you know, again, all the elements of A. Okay, in this problem we can't just finish here and return true because we don't know if another combination might be bigger than that. We just want to keep track of the max value we've seen so far. And you know, that's easy. It's the max of ai plus aj that we've seen so far. And then at the very end, we just return the max that we've seen. Alright, so this is O of n. This was O of n log n. And this is O of log n. So you can see that the n log n is what the complexity is. It's O of n log n to solve this problem. Alright, we can continue then to the case where we have 3 variables just in parallel. So we just did this first case. Second case, ai plus aj plus ak less than or equal to x again. And then it's the same exact idea, you know, we iterate over 2 of these, we look up the third, and the third is ak is less than or equal to x minus ai minus aj. And so we can write the same exact algorithm. We iterate over the first thing, so for I equals 0 dot 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 n minus 1. Iterate over the second thing, for j equals 0 dot 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 n minus 1. And then we look up the third thing again. So again, we need to have created a binary search tree, so it's a BST containing all elements of A. And then we can look it up, so find biggest number less than or equal to x minus aj, x minus ia minus aj. And, we update the max that we've seen before. And then at the end we return the max. So this is O of n, this is O of n, this is O of log n, this is O of n log n. And these three things kill the O of n log n, so we get an O of n squared log n complexity. Let's continue the pattern here. So we just finished this section here. We had an O of n here, n log n here. This just got multiplied by log n. O of n squared here, O of n squared log n. And you can see that in general it's going to be O to the nk minus 1 log n. Again, you'll see this over and over again. The fact that we had to deal with sorted information meant we couldn't look it up in constant time, we had to look it up in log n time. So that completes the second category of things I wanted to talk about. While we're on this less than or equal to sign, I just want to do a little bit of an aside. So if we do another problem down here, which also deals with less than or equal to information, say we're given k sorted lists of numbers. And we want to combine them all into one big sorted list of numbers that contain all the elements. What's the complexity of doing that? Well, we have sorted information, which means every number in each list is less than or equal to the previous. And so that's going to deal with a log n again. Alright, so how do we actually do this? The key idea is that there's less than or equal to information in all of these lists. So all of these implicitly have this less than or equal to sign between elements, and so the smallest elements are always going to be right here. And so we can just compare all of these to see which is the true smallest element. So we can compare the 1, the 4, and the 2. The smallest of those is 1, so we can just add 1 to this merged array. And then we can continue that process. We just used 1, so now we compare 3, 4, and 2. The smallest between those is 2, so we add 2. And we just keep incrementing the pointer. The smallest between 3, 4, and 9 is now 3, so we cross off the 3, and so on. And so how do we actually design an algorithm that takes this into account? Well, you have to realize that every single time we compare and then step, we're pretty much comparing the same elements. There's a lot of redundancy in what we're comparing. First we compare the 1, the 4, and the 2. And then we cross off the 1. Now we're comparing the 3, the 4, and the 2. Heaps are really helpful when you have to deal with taking the min of a collection of numbers, and so this is a perfect problem for that. So you can have a heap of all of the starting elements. So here it would be a heap of 1, 4, 2. You just heapify this, or whatever. And then you can pop the minimum element from the heap at each step and add it. So pop, add it here. Here is a 1. And then we add the 3 into this heap. And then we just continue. The heap is a O of log and data structure, and it has k elements. So each operation is O of log k, and we do it n times. We have n elements here. total. And so the full complexity is O of n log k. And once again, log k showed up because we had less than or equal to information.